Hello, hello. Okay. Um, so problem 6.13, it says the voltage across a 5 microfarad capacitor is known to be this equation right here. Uh, I listed all these parts into different numbers. So it start with number 1. It says find the current through the capacitor for t greater than 0. Assume the passive sign convention. Okay, so um, you gotta know first our capacitor equation. So our equation for our capacitor is we know that the current is going to be equal to the capacitance times the derivative of the voltage across the capacitor. So yeah, so we're going to follow this right here. So we take, well, this is now we're doing calculus, so we're going to take the derivative of VC and start with this. Right. And we are left with t e to the negative 2500 t, right? And then we here we want to apply product rule. For those who don't remember product rule, consider this u. V product rule says that our product rule will say u times dv dt plus v times du dt. So I'm going to do that. So 500, right? So t times negative 2500 e to the negative 2500 t plus 1 times e to the negative 2500 t. And this would be our VC. So then you want to find the current, right? You can just say 5 microfarad or 5 e to the negative 6. E to the negative 6 means 5 times 10 to the negative 6 times, and I can just write this value. Or let me it's hard to make handwriting look nice here, so here, especially on this. Okay. So this would be our answer for number 1. I'm going to go ahead and actually, yeah. So it says, so part 2 says find the power at the terminals of the capacitor when t equals 100 microseconds, right? So the power formula, since we know we have our I and our V with respect to time, we're going to use this equation, P equals V times I for our power equation. We could eventually we could calculate the resistance, but this is the easiest way. So our VC at 100 microseconds, right? 100 microseconds and 100 e to the negative 6. So we can just go ahead and plug this into VC 500 times 100 e to the negative 6, e to 2500, 100 e to the negative 6, which is which is 0.0389 volts. And if we plug this into ICT, I'm gonna we can make this 5e to the negative 6. So our result for this would be uh, oh, 5 to the negative 6. You get 0.00146 amps. Round it off there. So our power is going to be the multiplication of these two, and that would be 5.686. I'll round it off there. E to the negative 5 watts. It's going to be very little power. Yeah, it's going to be very little power. For part 3, it says, is the capacitor absorbing or delivering power? Since our power is positive, we're going to assume it's absorbing. That was an easy question. And then it's asking us, find the energy stored in the capacitor. So for part 4, our energy equation would be this: 1/2 C times V squared. So 1/2, our capacitance of our capacitor is 5 microfarad, so 5 to the negative e to the negative 6, and then our voltage at 100 microseconds is 0.0389 squared. So our result would be 3.968 E to -9 joules. And for our last question, it says, find the maximum energy stored in the capacitors and the time when the maximum occurs. So capacitors capacitors would essentially do is conserve potential energy. So voltage is once a capacitor reaches its max voltage, it turns into an open circuit, which means no current can pass through. So this all relates to back to voltage, right? So what we want to do is find the rates at which our voltage equals 0, or well, the derivative of our voltage equals 0. So we're going to go ahead and say dV over dt equals 0. We already know what dV over dt is. We have it here. Or I'm gonna right. So we want to equal 0 equals to 500 times -2500 t e to -2500 t plus e -2500 t. I'm gonna go ahead and just put this into an online calculator. So at the point, so at the time, the voltage reaches well, yeah, at the time, at these times, the times we're going to find here is where the capacitor will have its greatest stored energy, right? So let me go ahead and plug that in. 500 times -2500 t e to -2500 t plus e to -t, and then we want to make solve for t. Okay, so it's telling us that our t is going to be 4 milliseconds. So our t is going to be 0.0004, I believe. Yeah. T could also be 0. Making this t0 would make everything 0. If this was 0, 1, 1 plus, yeah, 0. Well, never mind. Anyways, this is where our voltage is going to reach its max potential. So VC at 4 milliseconds, or 40 milliseconds, sorry. I prefer to avoid milliseconds. I just rather have everything 1 unit. It's good practice though to have, I think. But anyways, we go back to the capacitor, the voltage capacitor equation, 500 T e to the negative. So we have 500 for 40 milliseconds. We're going to say -4 e to the negative 2,500 for e to the negative 4. That's going to give us 0.0736 volts. And then the maximum energy stored, once again, we use work equation. I'm going to plug that in. 5 e to the negative 6.0736 squared. That's going to give us give us 1.354 e to the negative 8 joules. So yeah, the max energy stored in the capacitor at the time when the maximum occurs is this value.